I've allowed you to record.
Yes, fine.
Okay.
Yes, I have started recording.
Yeah. Okay. Okay. So we've been talking about the solution of the Dirichlet problem for pre-compact domains with C2 boundary in a Riemannian manifold. So I thought maybe it's a good idea just to recap what we did, right? So because there were many steps in the proof of this. So step one is to prove to solve the Dirichlet problem for Poisson's equation in the okay, for the Euclidean Laplacian in the unit ball. So maybe let me call this delta naught. This is summation del squared del xi squared in the unit ball. Okay. So here we solve the problem equal to f e and u equal to y. Well, actually, u equal to 0 is good enough. So u equal to 0 on boundary B, okay, where F was alpha holder on the ball. U was C2 on the ball and C0 on the closure. Right, so this is the first result we proved. Yeah.
Yes.
And then using this, then we prove the method of continuity. So if you had a solution to the Dirichlet problem for the Euclidean Laplacian on a domain, then you also got it for any elliptic operator, second order operator on the domain, right? Okay, so solution for delta naught on a domain D implies solution for L on D. L was second order elliptic. Okay. So 1 and 2 together with this method of continuity together with part 1, so implied part 3, the solution of the Dirichlet problem for a general elliptic operator on the unit ball. Because for the unit ball, we already have the solution for the Laplacian, and then the method of continuity tells us solution for the Euclidean Laplacian implies solution for any second order elliptic operator L,
Yes.
right? So therefore, the solution of the Dirichlet problem for any elliptic operator L on the ball, the unit ball. Okay. And so this means, so here the solution we got was with appropriate boundary conditions. So say LU equal to 0 on B and U restricted to boundary B equal to phi restricted to boundary B, where phi we assumed was nice enough. It was in C2 alpha of B closure, right? Okay. So this was the solution for nice boundary values. Okay.
Yes.
And then by an approximation argument, we got the solution of the Dirichlet problem for L on a ball for general boundary values, right? So solution of so here we had LU equal to 0 on B, U restricted to boundary B equal to phi, and phi was just any continuous function on boundary B, right?
Right.
Yes, Utsav,
Yes,
is
sir.
this okay? Right. So once we had this, then we got the solution of the Dirichlet problem. So let me just write DP for Dirichlet problem in general. For the Laplacian on a geodesic ball in a Riemannian manifold, right? Because a geodesic ball you can identify with the unit ball in Rn, and then the Laplacian becomes identified with a second order elliptic operator on the unit ball, right? So we got the solution of the Dirichlet problem for the Laplacian geodesic ball in a Riemannian manifold. M. And once you have the solution for a geodesic ball, then this implies that you can define the harmonic lifting of a subharmonic function, right?
Right.
For that, you just need to be able to solve the Dirichlet problem on a geodesic ball. Okay. So therefore, we can define harmonic liftings. And once you define harmonic liftings, then you can use the Perron method, right? So Perron method for solution of the Dirichlet problem for the Laplacian on D, a domain in M, such that D closure is compact and boundary D is C2. So this solution of the Perron method, there were two main steps. One is to show that the Perron solution U phi, which was the pointwise supremum of functions in the Perron family, to prove this is harmonic. In the domain D. And then once we had this, then you need to show this Perron solution has the right boundary values. So for this, we used the fact that because the boundary is C2, at each boundary point, we have a barrier, right? So boundary D C2 implies for all xi in boundary D, there exists a barrier at xi. So remember, a barrier was a superharmonic function which was positive on D closure minus the point xi and 0 at the point xi, right? So it was a positive superharmonic function whose unique minimum is attained at the point xi, right? On the boundary. Yeah. I mean, superharmonic functions satisfy the minimum principle, right? That they attain their minimum on the boundary of the domain. There's some noise coming. Who's a lot of noise? Sound is on.
So my mic was on unmuted. Yeah.
Yeah, you just turn it off. Yeah, thanks. There's a lot of sound coming. Yeah. Okay, so once you have a barrier at each point, this implies that the Perron solution takes the right boundary values. So u phi of x converges to phi of xi as x in D converges to xi in boundary D. Okay, so is this all right? This is a recap of everything we did over the last few weeks. Yeah. Which solves the Dirichlet problem for any general precompact domain in a Riemannian manifold with C2 boundary. Right? So is this okay? Yeah.
Yes, sir.
Okay, so I mean, using the theory in Rn, what we did was basically solve in the unit ball for a general elliptic operator. Then that allows to solve in a geodesic ball in a Riemannian manifold. So that's like a local solution of the Dirichlet problem. And then you globalize that using the Perron method, right? To get global solutions on a general domain. That's the idea. Okay. So any questions about this? Utsav or Rudroda, any questions? Okay. So let me just prove one small thing which I mentioned last time, which is about subharmonic functions and the submean value property. Right. So let me make a definition. So suppose U is a continuous function on an open set in a Riemannian manifold. So we say U satisfies the submean value property So let me abbreviate this as SMVP. If for all x in D, for all R small enough, U of x is less than or equal to the average of U over the geodesic sphere of radius R around X with respect to harmonic measure based at X, right? So the average over the ball, the boundary of the ball of radius R around X, U of xi, D mu X comma D X R of psi. Right? Okay. Where for any y in M and where, okay, let me just say, where for any geodesic ball B in M and y element of B, mu y sub P denotes a harmonic measure on boundary B with respect to the point Y. Okay. So is this definition clear? Yes.
Yes.
So then we have the following proposition. The following are equivalent. So wait, let U be a C2 function on D. So then the following are equivalent. One Laplacian U is greater than or equal to 0 for all x in D. And 2 U satisfies the submean value property. Okay. Right. So proof of 1 implies 2 we've already done, right? Yes.
Yes, sir.
Yes, Utshab, is this okay? Yeah.
Yes, sir.
We've already done the proof of 1 implies 2. If you remember, how did we prove 1 implies 2? Well, we know that 1 implies the weak maximum principle, right? And then if you take any geodesic ball around a point X, you let H be the solution of the Dirichlet problem with boundary values equal to U on the boundary of the ball, right? Then you look at the function U minus H. The Laplacian of that is also greater than or equal to 0 in the ball B, because H, the Laplacian, is 0 and U, the Laplacian, is greater than or equal to 0. And so once the Laplacian of U minus H is greater than or equal to 0, then you get that U minus H achieves its maximum on the boundary of the ball. So on the boundary, U minus H is 0. So that means U minus H is less than or equal to 0 inside the ball. In particular, U of X is less than or equal to H of X. And H of X by definition is the integral of U with respect to harmonic measure on the ball with respect to the point X, right? So that gives the submean value property. Is that okay?
Yes, sir.
Yeah. Okay, so I'm not doing that. We've done this before. What was remaining from last time was the reverse implication, right? That if U satisfies the submean value property, then the Laplacian of U is always non-negative, right? This was remaining. Yes?
Yes.
Okay. So how do we prove this? So we prove by contradiction. So suppose not. So suppose that the Laplacian at some point x naught is strictly negative. Okay. Fine. So then, since u is C2, by continuity of the second derivative, the Laplacian will be strictly negative for all x in U, a neighborhood of x naught. Okay. All right. Yeah. So now choose a ball B equal to a ball of radius r with center x naught, which is contained in this neighborhood where the Laplacian is strictly negative. So the closure, B closure, is contained in U. Okay. Fine. And let H be the solution of the Dirichlet problem. So with boundary values U on the boundary of this ball B. So let H be C2 on B and C0 on B closure, such that Laplacian H equal to 0 on B and H restricted to boundary B equal to U restricted to boundary B. Okay. So then the Laplacian of U minus, well, or let me do it this way, the Laplacian of H minus U, this is strictly positive on the ball B, right? Yes, because the Laplacian of U is negative, so Laplacian of H minus U is strictly positive on the ball B. So, well, on this, yeah, on the ball B. So that's fine. So on the ball B. And so then that means by the weak maximum principle, H minus U is less than or equal to 0 on B, right? Since H minus 0 is equal to 0 on boundary B, right? Yes. Okay. So that implies that U of x, this is greater than or equal to H of x, right? Which is equal to the integral over boundary B of U xi d mu xb. But this, we're assuming U satisfies the submean value property. So this, on the other hand, this is also greater than or equal to ux, right? So this is because U satisfies the sub-mean value property, right? Yes?
Yes, sir. Right. Yes.
Is this
This is
Utsav, is this
Yes,
all
sir.
right? Okay, so then you have equality everywhere, right? So that implies what? So this is, sorry, at x naught, u of x naught is h of x naught. This is x naught. X naught is the center. So that implies that
u equal to h.
u minus, yeah, so h minus u of x naught is equal to 0. And that implies, by the strong maximum principle, right? That u is equal to h on B. But then u is harmonic on B. So that implies that Laplacian u is identically 0 on B. But that's a contradiction, right?
Yes. Yes.
Because we assume the Laplacian of u was strictly negative on this ball B, right? Okay, so that finishes the proof. Is this all right? Yeah.
Yes.
Yes, sir.
Rudrada, is this okay?
Yes, it's okay.
Yeah, okay. Okay, so that gives the equivalence between the Laplacian non-negative and the sub-mean value property, right? So therefore we can take the sub-mean value property as the definition of subharmonic for continuous functions, right? We gave another definition in terms of comparison with harmonic functions on the boundary of open sets contained inside the domain and so on. But this is maybe a neater definition in terms of the sub-mean value property, right? So we can take this as the definition. So I just wanted, this part was remaining from last time. So I just thought of this proof. So I thought I should just let you know. Yeah. Okay. Okay, so there's less about a minute left. So let me stop this session and we'll start another one. Okay, so that more or less finishes whatever I wanted to say about the Dirichlet problem. So just a remark, I mean, we have proved the solution of the Dirichlet problem for any domain inside a Riemannian manifold with C2 boundary, right? So, I mean, that domain may not embed into Rn, right? So it could be a domain like this, let's say. Okay, this could be your domain in your Riemannian manifold. So this is your domain D. And this is boundary D, which is C2. Yeah. So then you do have a solution to the Dirichlet problem in this domain, right? So that means just like we did for a geodesic ball, you can define the harmonic measure on the boundary of the domain D with respect to any point X inside. Right? So suppose D in M is a precompact domain. such that boundary D is smooth, or C2, say. Yeah. So then for X in D, right, we do what we did earlier for geodesic balls, define a linear functional T sub X from the Banach space of continuous functions on boundary D to R. Phi goes to U sub phi of X, right? Where U sub phi is the unique solution of the Dirichlet problem with boundary value phi. We know this exists, this U sub phi, you can take it to be the Perron solution, right? We know the Perron solution is the unique solution of the Dirichlet problem, right? So you can just take U sub phi to be the Perron solution. Right, so then the same argument as before, using the maximum principle, right, tells me that this will be a bounded linear functional, right, of norm less than or equal to 1. So then by maximum principle, mod T sub X of phi less than or equal to sup norm of phi, right? So the operator norm of T sub X is less than or equal to 1, and T sub X of phi is greater than or equal to 0 if phi greater than or equal to 0. This is also by the maximum principle. Right? Because for a harmonic function, it attains its infimum on the boundaries. So if the boundary value is greater than or equal to 0, then the function is greater than or equal to 0 inside. And finally, T sub X of the constant function 1 is the constant 1. So all this implies that norm T sub X is equal to 1, and the positivity of this linear functional implies that it's given by a, therefore, a probability measure. So T sub X phi is equal to integral over boundary D phi d mu x d for some unique. So this is for all phi in C0 boundary D. So this is for some unique probability measure. Mu xt on boundary D, okay, called the harmonic measure of the domain D with respect to the point X. Okay. Okay, so harmonic measures make sense for domains with pre-compact domains with nice boundary, with C2 boundary. All right. They are measures supported on the boundary of the domain. Okay. Okay, so not just for geodesic balls, they make sense for general domains. So is this all right? Yeah.
Yes, sir.
Yes, okay. So, okay, fine. So yeah, that's about the last thing I wanted to say about the Dirichlet problem for now. So now I want to move on to the next topic, which is the Harnack-Yau inequality. So this is very important. We use this in our discussion of harmonic measures, right? We used the Harnack-Yau inequality to show that the harmonic measures with respect to different base points were absolutely continuous with respect to each other, right? Okay. So we use the Harnack-Yau inequality there. Okay. So we'll be proving the Harnack-Yau inequality now. But before we do that, we need a little background, because there'll be some computations involving derivatives of tensors. So first, let's recall what is a tensor of order k. So abstractly, it's a smooth section of the vector bundle of the kth tensor power of the cotangent bundle. So what does this mean? That means that each point P, T sub P, is an element of Tp star m tensor power k. Now recall that for a finite dimensional vector space V, if I take V dual and the kth tensor power of V dual, that is naturally identified with the k multilinear functions, right? From V cross V cross Vk times to R, right? Okay. So this just means this as a tensor of order k just means that at each point P, I have a k multilinear map from the tangent space to R. Okay, a k multilinear function from the tangent space to R. So in particular, a differential form of order k is a tensor of order k. It's a special kind of tensor of order k where the multilinear function at each point is alternating, right? Okay. Okay. So we denote the space of k tensors, these smooth sections, by gamma of this T star n tensor power k. Okay. This gamma of any vector bundle E is the notation for the smooth sections of the vector bundle E. Okay. All right. So for T as a tensor of order k, for each point P and M, T sub P is a k multilinear map from T sub P, TPM power k to R. Okay. So for k equal to 0, the space of 0 tensors is by definition C infinity M, just functions. For k equal to, this is a typo, this is k equal to 1, the space of 1 tensors is just the space of 1 forms. Okay. And as we've seen earlier, the k tensors, these can be identified with maps from vector fields, cross vector fields, cross vector fields, k times to C infinity M, which are C infinity M multilinear. Okay, so remember the space of vector fields, this becomes a module, right, over the ring of continuous the ring of smooth functions, C infinity M. And then you want, as a map of modules, this should be linear, multilinear. All right. So if I multiply by a function, any vector field here, then that function should come out. Okay. So remember, the maps which are C infinity M multilinear, those correspond to tensors, right? Okay, these are local operators, right? So if x1 to xk are vector fields, then the value of t of x1 to xk at a point P only depends on the values of x1 to xk at P, right? Yes, so we've talked about this before, right? When we talked about the curvature tensor of a Riemannian manifold, right? Yeah. So should I explain this?
Fine.
Sorry?
Yes, it is fine.
It's fine, right? We've talked about this before, I think. We've talked about this before.
Yes, yes.
So you know
Yes,
what?
yes.
Okay, fine. So, right. So tensors, yeah, pointwise, they're just multilinear functions from the tangent space power k to r. And globally, you can think of them as maps from vector fields cross vector fields k times to C infinity m, which are C infinity m multilinear. Okay. Now what we want to talk about is the covariant derivative of a tensor. So how do you differentiate a tensor? Okay. So, well, let me give you a definition and then let me explain this definition a bit. So if I take a k tensor T, then its covariant derivative is going to be a k plus 1 tensor, nabla T. Okay. So this k plus 1 tensor, how is it defined? It's defined as follows. Nabla T applied to k plus 1 vector fields, right? It's a k plus 1 tensor, so it's going to act on k plus 1 vector fields. So I take k plus 1 vector fields in the form x1 to xk and then another vector field y. So this is defined to be y acting on the function t of x1 to xk. Okay, so t of x1 to xk is a function, right? It's a C infinity function, and y is a vector field, so it acts on this C infinity function. Okay, and then you subtract I goes from 1 to k t of x1 to xi minus 1, nabla y xi, and then xi plus 1 up to xk. So in the ith spot, you replace xi by the covariant derivative nabla y xi. Okay. And you define this for all x1 to xk and y in chi-m. Okay. So this definition looks very algebraic and it's not clear why we are defining this covariant derivative nabla t in this way, right? But one thing you can check is just algebra, is that the right-hand side here, this is C infinity m multilinear. Okay, and therefore it defines a k plus 1 tensor. Okay, so I mean, if I just took the first term y of t of x1 to xk, this is not going to be C infinity m multilinear. Okay, because suppose I multiply x1 by a function f, now that will come out of t, but y is going to act on the function f as well, right? So f, I mean, not only f will come out of this. So this first term is not C infinity m multilinear. So to make it C infinity m multilinear, what you do is you subtract these terms, all right? Then it becomes C infinity m multilinear. Okay, now that's if you want to think about it in a very algebraic way. Okay, that you're subtracting these terms so that this combination becomes C infinity m multilinear, all right? But geometrically, there's a simple way to think of the covariant derivative nabla t, which will explain this definition. Okay. So first of all, let me rewrite the definition in a certain form. So So let me rewrite it in this form. I have y acting on t of x1 to xk is equal to nabla t x1 to xk y plus sum I goes from 1 to k t of x1 xi minus 1 nabla y xi xi plus 1 xk. Okay, so here T is a K tensor. And this is for all x1, xk, y, which are vector fields on M. Okay. So if I rewrite the definition in this form, this should remind you sort of a Leibniz rule, right? In a sense, see, what am I doing here? I'm looking at T of x1 to xk, right? And then I'm differentiating it in the direction of the vector field y, right? Now, the idea is this derivative of T acting on these k vector fields, it should be like a Leibniz rule that first you differentiate the tensor T with respect to y. So that is the first term, this nabla T of x1 to xk acting x1 to xk and y. This is supposed to represent the derivative of the tensor, okay, with respect to y, and then you differentiate, and then you have T of the derivatives of the vector fields with respect to y. Okay, so this right hand side, this should look like a Leibniz rule. Do you see that?
Yes, sir.
Yes. Okay, now where is this coming from? So actually, if you want to think geometrically, how do you define the derivative of the covariant derivative of a tensor? So what you can think about is this. So you have your manifold, okay, and you have, say, the tangent space at a point and at another point along a curve, let's say, okay. So suppose I have a curve gamma. Okay. So then I have parallel transport along the curve, right? Which is identifying my tangent space, let's say at gamma 0 with the tangent space at gamma t, right? Yes? Okay.
Yes.
So now, what do I want to do when I want to differentiate a tensor? So a tensor is a multilinear function on each tangent space, right? So the thing is, at different points, my tangent spaces are different. So my multilinear functions are defined on different vector spaces. So I cannot compare them, right? So what can I do? Well, you do the natural thing. You identify one tangent space with another using parallel transport, right? So if I identify using parallel transport, then my multilinear function, which was over here, right, say t. So if I have from the tangent space at gamma t power k, I have my tensor t at gamma t, right? This is going to R. But now I can identify this with the tangent space at gamma 0 power k, right? How? Using parallel transport, right? So I take p sub t here, power k, right? Okay. And then I just compose. Okay. Is this clear? Yes? So then I get a multilinear function defined on a fixed vector space, right? The tangent space at gamma 0. So this
Yes.
in our
Yes.
earlier terminology, so this is a t gamma t composed with parallel transport power k. This is nothing but the pullback, right? This is pt star, the pullback of the tensor, right? T gamma t, right? Is this clear?
Yes. Yes. Yes.
Yeah. Okay. So this is an element of T gamma 0 star m tensor power k. Right? This pullback. Yeah. Now we can define. So given y a vector field such that yp equal to gamma prime 0. Okay. So where p is gamma 0. Okay. You define a k tensor which would be the directional derivative of the tensor t in the direction of y, the covariant derivative. So this is, I'm going to write this as nabla sub y t. Okay. This at the point P. This is defined to be what? This is defined to be ddt at t equal to 0 of pt star. Sorry, pt, the star is outside. Pt star of t gamma t. Okay. So see, this pt star of t gamma t, these are k tensors defined on the same tangent space, right? At TPM. So this is going to be an element of TP star m tensor power k. Is this clear? Okay.
Yes. Yes.
Right. These are defined on the same vector space. So therefore, I can differentiate these k tensors, right? Because they're k tensors on the same vector space. So therefore, those are elements. I mean, those are elements of a fixed tensor power, right? Tensor power of a fixed vector space. So therefore, I can differentiate them. Yes, it makes sense to differentiate now. And I define this to be nabla y of t. Okay, so this is again a k tensor. Okay, so thus given T a K tensor, and Y a vector field, we get nabla sub Y of T. This is also a K tensor. All right. Is this clear?
Yes.
Orkojit, is this okay?
Yes, sir. Fine.
Yes, all right, yeah.
Yes, all right.
Now, the K plus 1 tensor, nabla T, how is this defined? This is defined by nabla T of x1 to xk comma y. This is what you do is you first differentiate the tensor with respect to y. So you look at nabla y of t. So this is a K tensor, right? This nabla y of t. This then you act on these K vector fields. Okay. Is this clear? All right. Yeah.
Yes. Yes.
Yes.
Okay. Now, consider uh, uh, given y in chi m, okay, you let gamma be a curve such that gamma 0 equal to p and gamma prime 0 equal to y at p. Okay. Then let's look at this y acting on the function t of x1 to xk at p, right? What is this? This is by definition ddt at t equal to 0 of t at gamma t acting on x1 gamma t up to xk of gamma t, right? Yes?
Yes. Right.
Yes.
Okay.
Hmm.
Now, this we do the following. So, I write this as ddt at t equal to 0 of uh, yeah, so this is T gamma T of, so these x1 of gamma T and so on, I write as PT of PT inverse of x1 gamma T, etc. All right. PT of PT inverse of xk gamma T. Is this clear? Yeah.
Yes, sir. Right.
Now I have T gamma T of PT of some vectors,
Mhm.
right? So this is by definition, this is PT star T gamma T,
Hmm.
right? Acting on PT inverse x1 gamma T up to PT inverse xk gamma T. Okay.
Right.
Yes.
Yes.
Now note, now we have the following, that PT star of T gamma T, this is equal to TP plus T times nabla Y T at P plus little o of T, right? Yes. By definition of nabla Y T, right? Yes.
Yes.
Yes. Right.
And also we've shown for the covariant derivative of a vector field, we've shown that the covariant derivative of a vector field you can get by pulling back the vector field by parallel transport and then differentiating it in the fixed vector space TPM, right? So this PT inverse Xi of gamma T, this I can write as Xi of P plus T nabla Y Xi at P plus little o of T, right?
Right. Yes. Yes. Right. Mhm.
It's all
Mhm.
right, Utsav?
Yes, sir.
Yes, okay. This is by definition of
Covariant derivative.
the covariant derivative. Now, I just substitute these expressions for PT star T gamma T and PT inverse of Xi gamma T. I substitute these in here and then I expand by multilinearity. All right. So what will I get? So I'll get basically so this is going to be TP plus T nabla Y T of P plus little o of T. This whole thing applied to x1 of P plus T nabla Y x1 P plus little o of T up to xk of P plus T nabla Y xk of P plus little o of T. Right? So what happens when I expand? I'll get a constant term, Tp of x1 up to xk, right? So ddt at t equal to 0 of, so I'll get a constant term, right? Tp of x1p up to xkp plus, then I'll get t times what? So I'll get one term here, which is nabla yt acting on the x1s, right? X1 up to xk. Yes?
Yes, sir.
Yes.
Right.
Yt
Mhm.
at p acting on x1p up to xkp. And then what will the other terms in t be? There will be summation I goes from 1 to k. I'll get one t from here and then I let tp act on this. If I take the other term with t, then I'll get an order t squared term. So I ignore those, right? If I just look at order t terms, the first order terms, then they will come from these nabla y xi's and this tp,
Right.
right? So I'll get t sub p of x1 dot 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 nabla y xi and xk. Okay. And then the rest is big little o of t. Okay. And so when I take ddt at t equal to 0, the constant goes away and this little o of t goes away. I just get the t term. And that's exactly what I want. All right.
Yes.
Is it clear?
Yes.
This explains why you have this formula for the covariant derivative of a tensor. Is it clear?
Yes, sir.
Okay. So yeah, there's less than a minute. Let me stop and we'll continue maybe after a 2-minute break. Okay. All right. So let me stop this session now. Okay. Right. So just to finish this calculation, we get what we wanted, that this derivative becomes equal to the order t term, which is nabla y at t acting on x1 to xk at p plus some I goes from 1 to k, t acting on x1, I minus 1, nabla y xi, xi plus 1, xk at p. All right, is this clear? So it is really a Leibniz rule, right? Yeah, this thing is equal to y applied to t of x1 to xk, right? This is y applied to t of x1 to xk. So what you do is basically you think of it as you differentiate t with respect to y. That gives you the first term here, right? This is differentiating t with respect to y, keeping x1 to xk fixed. And then you keep t fixed and differentiate each xi with respect to y, right? Is it clear?
Yes.
Yes, sir.
Yeah. And so you get it from this geometric definition of the covariant derivative of a tensor, where you just do the natural thing, right? You want to differentiate a tensor along a curve, but the problem is along the curve, the tensor takes values in different vector spaces. So what do? You identify those vector spaces using parallel transport, so that the tensor takes values in a fixed vector space. Then once you're in a fixed vector space, you can just differentiate in that fixed vector space. You define that to be the covariant derivative of your tensor, right?
Right.
That's what we're doing. Then once you do this, then you see that this formula that we took as a definition for y of t of x1 to xk, it drops out naturally, right? It drops out naturally from this definition of covariant derivative using parallel transport. I mean, the covariant derivative of a tensor using parallel transport, it drops out in a very. Okay, okay, so that this was just some. So this should give you now, I mean, motivation for this definition that we gave, right? This abstract definition here, which was seemingly unmotivated. Now, does it make sense now,
Yes, sir.
this definition?
Yeah.
Yeah, okay. Okay. So this is how one defines the covariant derivative of a K tensor as a K plus 1 tensor. Okay. So for example, if we take a 0 tensor, so that's just a function f in C infinity n. So then its covariant derivative nabla f, it's a 1 tensor. It's just going to be the one form df, right? It's just going to be the one form df. Now, what about the 2 tensor nabla df? So df is a one tensor. So its covariant derivative nabla df is going to be a 2 tensor, right? So how is this 2 tensor? What does this look like, right? So by definition, it's given by the following. If xy are vector fields, then nabla df acting on xy is what? It is, by definition, y of df of x minus df of nabla yx, right? That's from this definition up here.
Yes.
Yes. Y of t of x minus t of yx, right? Where t is df here. Okay, so it's y of dfx minus df of nabla yx. Now, what is df of a vector field x? By definition of the gradient vector field, this is the same as the inner product of grad f with x, right? And this df of this is the inner product of grad f with nabla yx.
Right.
Now, we use the compatibility of the metric, this y acting on this inner product grad fx. This is nabla y grad f inner product x plus grad f inner product nabla yx minus this nabla grad f nabla yx. So these two terms cancel. So we get simply nabla y nabla f inner product with x. And this, if you remember the definition, this is nothing but the Hessian of f acting on xy, right?
Yes.
This is just the definition of the Hessian. So therefore, for a function, if I look at its second derivative, its second covariant derivative rather, that is nothing but this nabla df. This is nothing but the Hessian, nabla squared f. Okay, this is the Hessian of f. Okay, so now let me just make this remark. You see, in Euclidean space, right? In Rn, for a function f in C infinity Rn, we had its covariant derivatives, right? Its covariant derivative, sorry, it's just its higher derivatives, not covariant derivatives. Its derivatives were dkf, right? Which at each point, this was, what was this at any point P? This was a K multilinear map, right? From Rn cross Rn K type R, right? Okay. So these were the higher derivatives of a function in Rn, right? So similarly, in a manifold, what are the higher derivatives? In a Riemannian manifold, the higher derivatives are going to be these higher covariant derivatives, right? Okay, we have the first derivative. So you think of this f and c infinity m. This is the zero tensors. Okay, so we have so grad f equal to df. This is one tensor. The first derivative is a one tensor. Okay. And then the kth derivative. What is the kth derivative of a function? Kth derivative is nabla k minus nabla kf. This is nabla k minus 1 of the one form df. Okay, this is going to be a k tensor. Okay. Okay, so this generalizes what we did for higher derivatives in Rn. This generalizes higher derivatives to a Riemannian manifold. All right. Where you take these higher order covariant derivatives, these become k tensors. Okay, just like in Rn, the higher derivatives were k tensors on Rn. Similarly, on the manifold, the higher derivatives of a function are k tensors on the manifold. Is this clear? Okay.
Yes.
But for this, you need a Riemannian metric. You need a Riemannian metric. If you don't have a Riemannian metric, then the higher derivatives are going to become much more complicated objects. I don't know if you understand that. You see, without a Riemannian metric, what would happen to the higher derivatives? So without a Riemannian metric, the situation becomes much more complicated. Without a Riemannian metric, what happens? You get that df, this is a vector bundle map from the tangent bundle Tm to R, right? Yes?
Yes.
This is a smooth map from Tm to R. Now, where will the derivative of this live? So d of df, the second derivative, this is going to be the derivative of this map. This is going to live on the tangent bundle to the tangent bundle, right? Taking values in R. Okay. Now, the tangent to the tangent bundle, this is a much more complicated object. Okay, and then this would be the second derivative. The second derivative, the third derivative, d of df. This would be a horrible object. This would live on the tangent to the tangent to the tangent bundle. Do you understand?
Yes, sir. Yes, sir.
So these would live on very complicated spaces. You're basically taking iterated tangent spaces. So that's much more complicated. Do you understand? Here we're looking at what the base manifold is fixed. The base manifold is fixed. And we're just looking at higher and higher ranked vector bundles on the same manifold. Right? But here the manifold itself is changing. I mean, the base manifold itself is changing, right? Tm is a vector bundle over M, but TTM is a vector bundle over Tm. And TTTM is a vector bundle over TTM, and so on. Do you understand?
Yes.
Okay, so if you didn't have a Riemannian metric, then these higher order derivatives become horribly complicated objects. Okay. right?
Right.
Okay, so think about this. This Riemannian metric is making life okay, by allowing you to take covariant derivatives of tensors, and then the higher derivatives, they become just like in Rn. They're all tensors on the same fixed space, right? They're just tensors of different orders. Yes. Okay. Okay, so yeah, think about this a bit. This is not so. Yeah. Okay. So, all right. So to come back towards the Harnack-Yau inequality, what we'll need is a lemma about the third covariant derivative of a function. Okay. So notice that the second covariant derivative, this is the Hessian. We proved that the Hessian is a symmetric bilinear form, right? It is symmetric in xy. We proved that. The third derivative is actually not going to be a symmetric tensor. So notice in Rn, our higher derivatives were all symmetric tensors, right? Yes?
Yes.
If you recall, the higher derivatives of a function on Rn were symmetric tensors. These were symmetric tensors. Okay. So these were symmetric tensors. This is the kth derivative is a symmetric k tensor. In a general Riemannian manifold, this kth derivative is not symmetric in general. It's only symmetric for k equal to 2. The second derivative is symmetric, but the higher derivatives are not symmetric. Okay. In fact, what happens is some curvature terms come when you look at the higher derivatives. So let me explain that. So this next lemma will tell you the following. So let f be a C infinity function on M. Then for all vector fields x, y, z on M, we have, so nabla cubed of x, y, comma, z is the same as nabla cubed f of yx, comma, z. So it's symmetric in the first two variables, okay? This is like the symmetry of the Hessian in the first two variables. In fact, it comes from the symmetry of the Hessian in the first two variables. So it's good in the first two variables, it's symmetric, all right? But what happens if I switch the last two variables? If I interchange y and z, then what happens? Nabla cubed f of x, y, z is nabla cubed f of x, z, y plus a curvature term, r of y, z, grad f, x. All right? So this shows you the asymmetry of the third derivative. Okay, in Rn, you don't see this because in Rn, the curvature tensor is 0. So this term vanishes in Rn. You see? Okay.
Yes.
All right. So first, let's prove the first property. So property 1, recall that the Hessian nabla squared f is symmetric, right? So nabla squared f of xy is the same as nabla squared f of yx. Okay. Now, by definition, what is nabla cubed f of x, y, z? So this is going to be z of nabla squared f of xy, right? Minus nabla squared f of nabla zx, comma y, minus nabla squared f of x, comma nabla zy, right? Yes? This is by definition of the
Yes. Yes.
covariant derivative of nabla squared f. Right, nabla cubed f is nabla of nabla squared f. So I'm just using the formula for nabla t, right? Okay. Now, this nabla squared f of xy, this I can interchange the x and y, right? Because nabla squared f is symmetric. So this first term is the same as nabla z acting on nabla squared f of yx.
Right.
Okay. And then I have this. So I bring this term. Yeah. So this term, also this term, I interchange the x and the nabla z y, and I bring this here. So I get minus nabla squared f of nabla z y comma x.
Mhm.
Okay. Minus nabla squared f of, I interchange the y and the nabla zx
Right.
here again. Y comma nabla. Okay. And this, by definition, if you look at it, this is the definition of nabla cubed f of y comma x comma z, right?
Yes, yes.
Do you see? Yeah, this is the definition of nabla cubed f of y comma x comma z. So that proves the first part, all right? Is this okay?
Yes, sir.
Yes.
Okay. So now let's come to the second equality. Okay. So we write down first nabla cubed f of xyz. So we have the formula for this from before, and also we have this formula for, by definition, nabla cubed f of xzy, right? So that's going to be y acting on nabla squared f of x minus nabla squared of nabla yx z minus nabla squared f of x comma nabla yz. All right. Now we use the symmetry of the connection of the Levi-Civita connection. So we know that nabla sub yz minus nabla sub y is equal to bracket yz. Okay. So therefore, if I look at this first line minus the second line, what do I get? Nabla cubed f of xyz minus nabla cubed f of xzy. Look, this difference is what I'm trying to get a formula for, right? I want to show this is equal to a curvature term, right? That's what my part 2 says. This minus this is a curvature term, right?
Right. Yes.
So that's why I'm looking at this difference. I want to show this minus this is a curvature term.
Mhm.
So I use the definitions of these two. So it's this right-hand side minus this right-hand side. Okay, so I group the terms together. So what will happen? I'll get this z nabla squared fxy minus this y nabla squared f. That's the difference of these two terms. Then I suppose I have the difference of this term and this term. So I'll get a nabla squared f of nabla y x comma z minus nabla squared f of nabla z x comma y. That's these two terms. And then I have these two terms. Now these two terms, when I take the difference, what happens? This x is common and I'll get a nabla y z minus a nabla z y, right? Yes? Or I'll get, yeah, so I'm taking this minus this. So I'll get plus nabla yz minus nabla zy. That is exactly the bracket yz, all right?
Yes. Right.
So the last term will be nabla squared f of x comma bracket yz, all right? Yeah?
Yes. Right.
Is
Mhm.
this? Now let's compute the first term appearing here, this z nabla squared fxy minus this y nabla squared fxz.
Mhm.
Okay. So here we use the definition, we use the fact that nabla squared f is the Hessian, right?
Mhm.
So when I look at this z nabla squared f of xy minus this y nabla squared f xz, this nabla squared f of xy I can write as the Hessian, which is inner product of nabla y grad f with x, right?
Mhm.
And similarly, this nabla squared f xz I can write as inner product of nabla z grad f with x, right?
Right. Okay.
Now I use the metric compatibility.
Mhm.
So z acting on this inner product will be a sum of two terms
Mhm.
minus y acting on this inner product will be a sum of two terms, right?
Right. Right.
So what will I get? I'll get nabla z nabla y grad f x plus grad y nabla y grad f nabla z x minus Here I'll get a nabla y, nabla z, grad f inner product x minus nabla z grad f, nabla yx, right? This y is going to act on the x here. So, okay, great. So the terms with x common, I have these two terms, the first and the third term with x. So I group those together and I get this term inside here, right? So that gives me something like a curvature term, right? I get a nabla z, nabla y minus a nabla y, nabla z, right? This thing acting on grad f. You see? Yes?
Yes.
Yes, sir.
Okay, and then I
Mhm.
have other terms. Okay.
Mhm.
So let me just look at curvature term now. So this term by definition, this is equal to the curvature tensor R of yz plus, minus nabla bracket yz, right? The whole thing acting on grad f. You see?
Yes.
Right? This is by definition of the curvature
Mhm.
tensor. Yes?
Yes.
This is by definition of the
Yes.
curvature tensor.
Yes. Yes. Mhm.
So this gives me the curvature term that I want. Okay. And then minus I get this nabla of bracket yz, grad fx, and then I have these two other terms. So this second term here, this is nothing but the Hessian acting on x comma bracket y,
Right.
right?
Right.
So I get this minus the Hessian acting on x comma bracket yz. Now that is going to cancel with this plus the Hessian acting on x bracket yz in this first equation.
Mhm.
You see?
Right.
Right? So I expanded out this first term here. I got this expansion, and then one term from here is going to cancel with this term, and then these two terms are going to cancel with these two terms. Okay, so that's what happens. All right. So you substitute this expression in the first equation and you cancel terms and you get exactly what you want. This is this curvature. This difference is equal to this curvature term. All right. Is this clear? Yes.
Yes.
Okay. So
Yeah. Yes.
we started with this difference. We wrote it as a sum of three terms, right? Now, the first term here, this z nabla squared f minus this y nabla squared f, this thing I expanded, right? And after you expand this, you'll get a curvature term and then minus some term and then plus another two terms. So this term with the bracket yz is going to cancel with the term with bracket yz here. They come with opposite signs. And these two terms are going to cancel with these two terms here. You see? Over here, I've got a minus nabla squared f, nabla zxy. Here, I've got a plus nabla squared f, nabla zxy. So this cancels with this. And here, I've got a plus nabla squared f, nabla yx, comma z. Here, I've got a minus nabla squared f, nabla yx, comma z. So they cancel. Is that clear?
Yes.
Yes? So everything cancels. All that remains is the curvature
Right.
term.
Right.
Okay? Okay.
Yes.
So that proves the formula. Okay. That proves this formula. Okay. So now let me define what is called Ricci curvature. So the Ricci curvature. So remember the curvature tensor that you could think of as a 4 tensor, right? It acts on 4 vectors, right? If I take 4 vectors, the Riemann curvature tensor, I can think of as a 4 tensor, right? Curvature tensor. R can be viewed as a 4 tensor. Right, what is the 4 tensor? It's just if I have 4 vector fields, say VW XY, then you get a function inner product between R of VW acting on X, inner product with Y, right? So this is a 4 tensor. Yes?
Yes.
Is this clear? Okay. Now, from this curvature tensor, it turns out that various combinations of the curvature tensor, they lead to other important tensors of lower order, which are also important in geometry. So one of these is called the Ricci curvature. Okay. So what is the definition of the Ricci curvature? So the Ricci curvature is a 2 tensor, all right? So that means it acts on 2 tangent vectors or 2 vector fields. Okay. So how is this defined pointwise? So pointwise, what you do is the Ricci curvature at P acting on 2 tangent vectors VW is the following. So first of all, if I have 2 tangent vectors VW, then that gives me a linear map from the tangent space to itself. What I do is I put V and W in the first and third slots of the curvature tensor. And then I have a linear map. Z goes to R of V comma Z acting on W. So this is linear in Z, right? Okay. So this is an endomorphism from TPM to TPM, right? Yes.
Yes.
So then we take it. Then we take its trace. We take its trace. All right. We take its trace and we divide by n minus 1. Okay. So this is the Ricci curvature. Is this clear? So this is a 2 tensor,
Right.
right? It's a multilinear function. It's a bilinear function of V and W.
Hmm.
It's a bilinear function of V and W,
Right.
right? Now, what is this trace? Well, the trace is what? Trace of a linear map T with respect to an orthonormal basis is just sum over I, inner product TEI with EI, right? That is the
Right.
trace. So I just replace Z with elements of an orthonormal basis EI. So then this becomes 1 over n minus 1, summation I goes from 1 to n, inner product R of V comma EIW with EI, right?
Hmm. Right.
Okay. Now, so one thing I should say is from the symmetries of the curvature tensor, okay, one can show that this Ricci tensor is a symmetric tensor. So it's a symmetric bilinear form. Okay, it's a symmetric bilinear form. So R of Ricci of VW is the same as Ricci of WV.
Hmm.
Okay, so that follows from the symmetries of the curvature tensor.
Mhm.
Maybe we've done enough to prove it, I think. So one second, let me just think. No, no, that needs a proof. Yeah, I don't think we've proved it, but it's a fact. This is a symmetric bilinear form. Therefore, it is determined by the quadratic form, right? Ricci of V comma V. That's a quadratic form. So, so I need to understand what is that quadratic form, Ricci of V comma V. All right.
Okay.
I just need to understand that. So for that, let me first take V to be a unit vector, right? So if V is a unit tangent vector, then what we can do is we can extend V to an orthonormal basis V comma E1 up to En minus 1, right? Okay. So then in this sum, what happens? The first term, when the first element of the basis is V, this R of V comma V is 0, right? Because the curvature tensor is skew symmetric, right? So in its first two, it's alternating in its first two arguments. So the first term will vanish, right? And so then I'll just get sum of the other terms, right? I goes from 1 to n minus 1, ei comma ei, right? Is this clear?
Yes, sir.
Yeah. And what is this? This is nothing but a sectional curvature, right?
Right.
This R of V comma ei, V inner product with ei, this by definition, this is a sectional curvature. This is the sectional curvature of the span of V and ei, right? This is sectional curvature of the span of V and ei. So therefore, this Ricci curvature acting on V comma V is nothing but an average of sectional curvatures. All right? It's an average of sectional curvatures of two planes which contain the vector V. All right. So in 3 dimensions, the Ricci curvature acting on V comma V would be, if this is V, and then your orthonormal basis is V, E1, and then E2, right? So then basically you have these two planes containing V, the span of V and E1. That's this plane. And then you have the span of V and E2. That's this plane. Right? So you have this sigma 1 is span of V and E1. And you have this sigma 2 is span of V and E2. Okay, you see in the picture, yeah? So, right, so it's like this basically.
Yes.
And this plane. So you take the Ricci curvature, and this direction is V. Ricci of V comma V. If it's a unit vector, it's just the average of these two small curvatures. So this is in 3 dimensions. And this is as if V is a unit vector. If it's not a unit vector, then you just multiply by norm V squared, since it's homogeneous of degree 2, right? Okay. Is this clear?
Yes, sir.
Okay. All right. So we're out of time. Let's stop here for today, and we'll continue on Thursday. Okay.
Okay.
Okay.